I can and Jordan and the other one is
Alright guys, time to start. You ready?
Yes, sir.
Okay, let's do it. Previously, we talked about Gaussian elimination. I talked about order theory. We covered NumPy and everything about NumPy already. Almost everything, not everything, okay? So now, we talk about Gaussian elimination. And now we will focus a little bit more on why do we do partial pivoting, okay? When there's 0 in the diagonal term, you will end up with something divided by 0. So this means we need to swapping the row. Okay, we have to swap the row. So what I do is max at diagonal, okay, to find where's the maximum. Then for each step, I swap the row to make sure that the diagonal term has the maximum value. Okay, so I start with my random matrix. See, cell 91, that one create a random matrix. Then I try to replace something to 0, okay? I put A2 to 0, 0 equal to 0. So look at A2 in output 98. You see 1, 1, 0, 0 and 1, 1, they are equal to 0. And some row here, that's 0 too. So what happens if you just use Gaussian elimination? You divide it by 0, it doesn't work. Okay? So this means step 1, I take the absolute value of everything and then I swap the row. I put this row as the first row, swap it, and then it's fine because the diagonal term is not 0. Okay? And then I do Gaussian elimination. After I do Gaussian elimination, the second one, that's to 0, so I have to swap the row again. This method is just swapping the row, not the column. We call it partial pivoting. If you swap the row and swap the column, that's a full pivoting. So that's the idea. Okay, swap the row. If we don't swap the row, look at what happened. I get NaN, not a number. Okay, so that's not good. So I have use a Gaussian solve partial pivoting. Okay, with partial pivoting, what you see here is, first step is A equal to NPH stack. So this is to append everything to the right. Okay, append B to A. And then we have for K in range of n minus 1, max index equal to A K colon comma K dot argmax plus K. I need plus K because every time you see K start with 0, right? And then K will become 1, K become 2, 3, 4, 5 until n minus 2 because range is exclusive for n minus 1. So if you search for the range of from row K to the last row, okay? So if K equal to 1, it search from row 1 to the last row. That's the purpose, okay? Comma K mean K column. So it look just row, it look just diagonal term, okay? And it find out any term below the diagonal term, which one is the highest, where's the maximum. Once I get the maximum, then I swap. Note that if we start if we have slide k colon mean if k equal to 1 mean that row to the end, right? So let's say the maximum is minus 5. Maximum of absolute value is minus 5. So that is what row? It doesn't return the absolute row number, but it returns the relative row number. So it starts to count that as row 0, row 1, row 2, row 3, row 4, row 5, row 6. The absolute value is row 7, right? But that dot argmax give us argmax. It doesn't know anything about the absolute value because it take this array. It just take that array and have to return argmax. It just take AKK, you see? So when our slice of matrix A start at K, so that starting point is row 0. Okay, argmax becomes 0. So there's no way that you will understand the whole code right away. So this homework on Wednesday will be very easy. You will be asked to just run this whole code, and you'll be asked to use the code to solve something. And you can use my code, or you can write your own code if you want to. Doesn't matter. If you use my code, you say, where does that come from? Which cell? For example, this one is cell 102. You say it's from 102. Okay. If you use other people's code from the internet, you include the URL. Okay. So the purpose is for you to understand the step, and I already give the code. Use it. All right. So first step is find the max argument, the index of the maximum argument on the diagonal term. And then you see A bracket K max index equal to A bracket max index K. See that? That is to switch the row. After it switch the row, then we can do the regular procedure. Those 3-4 lines, when I say regular procedure, what is that? Is that you have two choices. Backward substitution, or maybe 3 forward substitution, or what? Daniel, what are those 3 lines? 4 lines. Start with for I in range k plus 1 n, I equal to minus a over a. What's that? Daniel, come on.
So I don't know. But so actually,
What is that?
So I don't.
Guess.
It's the same formula for as Gaussians.
Gaussian elimination. Very good. It is. How can you know?
It looks like that.
By looking at it, right? How do you know for sure? You use the method that I taught you last time. Extract some part of the code, put it in a cell, and run it. I can tell you that's how I get to understand it. How can you understand it? You do that. I won't force you to do that, hold your hand, move your hand. No, I don't do that. You have to do it, okay? So those 3 lines is Gaussian elimination. Make bottom left to be 0. And then we have outside the for loop. Okay. Daniel's second chance. What are those? Ami, what are those 3-4 lines? Geraldine.
This is.
Oh, you have answer? What's that?
I'm thinking actually.
Okay. Jer?
LU decomposition.
Oh, we are not at LU yet.
Back substitution.
Oh, very good, Mr. Prodamo. Is this a back substitution? You must know it, even though you don't. Okay, come on, we do Gaussian elimination. The first step is elimination. The second step is substitution. Please, 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 please. You must know it, okay? So when we return what? What's that? A colon comma n bracket colon comma new axis. So we return a comma n colon comma n. That means every row, right? Every row, but only on column n. Good.
Yeah.
The first one over there. Just that mean every row, just column n. Column n is the answer, isn't it? But when you write something like that, it returns a vector of the dimension n, comma, nothing. You remember the shape of vector? Vector just n, comma, and nothing, right? But you don't want that. You want to make it as vertical vector. I mean, vertical matrix like that. So that's why you have colon, comma, np.new axis. So that is to make your horizontal matrix to be vertical one. Just that. So that's how you get this as a vertical vector. Otherwise, you're going to get 0.773 something, comma, minus 1.0, comma, 0. So it's become horizontal matrix. Okay? So if you cannot absorb everything right away, how do you know it? You take some time to code, run it, and find out what it is. The code is there. You need to know it. And I cannot test you without a computer to see if you know it or not. But every Wednesday, we will take a class in the computer lab. At that time, I can test you. If there is any quiz, it should be on Wednesday. Okay. If it is on Monday, you do the quiz on the paper. If it is on Wednesday, you do quiz in that group. And as of right now, I will need to test, but I have been told that you have access. Each of you have access to 212. So what you might want to do before the quiz, if we have the quiz on Wednesday, is try to turn on the computer and open Jupyter Notebook and run and see if it runs or not. And when you go to that room, make sure that you stay apart from each other, because the final exam, I will move it from Monday to Wednesday on the same week so that you can do final exam. Oh, we don't have final exam. Exam 2 with computer. So this way may be better. Previously, we really cannot do it, but okay, right now we just have this many numbers, so we can do it. Alright, that's done with partial pivoting. Partial pivoting, it do a lot to you, but we just add couple more lines. 1, 2, 3, 4, 5 lines, 4, 5 lines, just that.
Professor, can
Oh, actually, it's 2 lines. It's just 2 lines. Yes.
Can you tell me again why are we doing partial?
Partial pivoting is, you see formula for R. R is minus aik divided by akk. Okay. If absolute value equal to 0, you end up with what? Divided by 0. Which is not cool. You get not a number, NaNn. You get that, you see? Nan. You don't want that. Your matrix have some location 0 on the diagonal term. You don't want that, do you? So this means for the first run, you see the first row, you check, okay, where's the maximum index? Maximum index happen at -6, that's the first index. Then you swap the whole row with the first row, with row 0. Okay? That's when swapping occurs. And it's nothing more. You just add what? 2 lines.
So,
Don't count the comment. You just add 2 lines. Gaussian elimination, the format of it is 3 nested for loop, right? You have loop K, loop I, and loop J. 3 nested for loop. So before you calculate any R, you swap. Once you swap, you move on. The part that you already done, you don't, let's say you finish with row 0. You move on to row 1. You move on to row 2. At row 2, you need to swap. You swap, then you move on to row 3. Whatever you pass already, you don't put it in the domain of swapping. Okay? That's why when you swap, you start from AK colon, not just A colon. Question? No question anymore?
No, there's a- like, can we still get the pivot, like without using the maximum number?
The question is, can we still do pivoting without looking for the maximum number? We can. It's not the best. Actually, the one on the diagonal, it can be anything other than 0, right? So we don't need to use maximum number. The reason that we use the maximum number is that it gives us minimum error. So if the diagonal term is not maximum, you have high error. If the diagonal term is the maximum value, you have minimum value. Okay, let's say homework for this week. This week, you are asked about how many times that we have to do calculation. How many times do we have calculation? What is the time complexity? When you are asked about time complexity, what you do is you count the number of calculation of the, oh my god, it's the screen is blinking. So you put the counter in the most inner loop. So we have loop K, loop I, loop J. You put your counter in loop J and you count how many times that the calculation happened. Okay? So in addition to line Aij equal to Aij plus Rakj, you put one more line, counter equal to counter plus 1. Okay? And you initialize counter outside the loop, say counter equal to 0. So that way you can count how many times that the calculation happened. Is that n squared? Is that n cubed or what? So that roughly tell you the time complexity as n approach like infinity or the big number. Okay. So if you would guess the calculation, the amount of time that the calculation occur will be 3 nested for loop. 3 nested for loop plus 2 nested for loop. So the back substitution is not the slow step. You see? Why is that? Because it has just 2 nested for loop. Okay? So if you have 1 million plus 20, for the sake of simplicity, we say, okay, the order of magnitude is about 1 million. We just neglect that 20. Something like that. So the first one is kind of n cubed. The second one is just back substitution is just n squared. So here the slow step is not Gaussian elimination, but the slow step is
Back substitution.
Oh, I'm sorry, my fault. The slow step is not back substitution, but it is Gaussian elimination. Gaussian elimination has 3 nested for loop. So that's the slow step. If you have many for loop, that's the slow step. It's not exactly n cubed. Why? Because we don't do 0 to n every time. We do 0 to n and then k to n. So we didn't do the whole thing, right? And then we do k plus 1 to n and then k plus 1 to n again. So we didn't do the whole thing, but it's still kind of 3 nested for loop. So if your answer is more than n cubed, it's wrong. Okay, it should be less because we didn't do the whole 0 to n.
But I could answer n cube.
It depends. Actually, you can just do Wikipedia and it tell you exactly what's the time complexity or the. Alright. So that is Gaussian elimination with partial pivoting. Everything is the same except you add 2 more lines. It's a lot more powerful. You see it? Alright. So I compare my result with linear algebra.solve. So you have to import from scipy.optima or what's that? From scipy import linear algebra or something. So So that line is to check with to get answer from scipy. You need to know how to do that too. Okay, when you use .solve, probably maybe it's faster than what I did. Okay, just solve the linear algebra without telling you what method I use, but you can know the method by read the whole documentation. So it's just solve, and I compare the error from A2 dot dot A2 dot dot answers from scipy minus B. Basically, when I finish, I have to substitute the result in, do AX, and check if left hand side equal to right hand side or not, right? And they are equal to each other. So error from scipy and error from user or from me, they are same order of magnitude. Okay. Checking the condition number A. Okay, condition number has to do, will tell you what kind of system of linear equation you have. If it is a well condition, the condition number will be 1. If it is ill condition, it will be a very large number. Let's say if you have system of linear equation n by n, but every diagonal term it is 0. Can you solve it? No, you cannot solve it, right? Okay, so this condition number tell you how easy or how difficult that the linear system will be. And if it's close to 1, this means your error is low. If it's more than 1, a lot more than 1, this means your error is high. Okay, so if condition number is low, it means it's easy. How do we calculate the condition number? For A, x equal to b, if x changed a little, so if A contains a small error, what will happen to B?
Small error.
Okay. You see matrix A, x change a little. What is x change a little? Ax equal to b. Why do we talk about little change in x? Because your answer is not analytical solution, is some solution plus the uncertainty of probably 15 digit. Okay, you have 15 digit accuracy, so your number is not exact. So let's say your number is 1/3. You don't get 1/3, you get 0.0, or you get 0.3333333 15, 16 times, and then done. You don't get the whole to infinity. So you have some truncation error, right? So we want to know if a little bit of error in the answer or a little bit of numerical error, is that going to propagate a lot or not? So from Ax equal to b, we say, hey, instead of just x, just have x plus delta x. Okay? So your answer will be b plus delta b, correct? So if you have a little bit change in x, you have a little bit of change in b. So you know that a delta x equal to delta b. Alright?
Why what? Equivalence?
Just that line. So this line, we have b plus delta b. B is ax, so delta b must be a delta x. Right? Okay. Now then, from the second equation, we divide it by a, the whole equation, or you multiply by a inverse, and then you divide it by x, and you will see double line. That's the norm of the matrix. There are several kind of norm, but norm that we use is everything square, add together, and then take square root. It's like a length of the vector. Okay, so delta x over norm x equal to a inverse delta b over norm x. Okay, norm of something multiplied by something will be less than norm of individual thing multiplied together. So this means norm of a inverse multiplied by delta b will be less than norm of A inverse multiplied by norm B. This is a mathematical rule. Okay. Do the math. You review it by yourself. Once we do the math, okay, I skip one line and then I get delta x over x. So relative error in x will be less than or equal to norm of A inverse multiplied by norm A multiplied by norm of delta B over B. So this is the relationship between a little bit change in x. What will it do to the change in B, right? So basically, if we have a little bit change in x, the change in B will be, okay, less than 1 over condition number. Condition number is norm of A inverse multiplied by norm A. So norm of A inverse multiplied by norm A, that tells you how easy it is. If your system is not easy, this means a little bit of change in X cause a lot of change in B. So it's not stable. So we should find the condition number. Okay? Condition number equal to 1 means it's easy equation. How do we find condition number? NP, okay, numpy dot linear algebra dot con, cond, and A. Then it tells you condition number. Ta-da! Done. Very easy, right? To tell condition number. Fact of the matter is, to tell the condition number, you need to know what is A inverse. Okay. A inverse is what you're trying to calculate, right? Or you actually don't know. I haven't covered how to calculate A inverse yet, but basically, you need to know the solution first before you tell how difficult it is. Okay, like you don't know how difficult the task is until you do it or something. One way is to do this. Another way is to calculate A inverse and multiply by get the size, the norm, and multiply by the norm of A. So I do this kind of test, okay. I add, look at this. I make the diagonal term to be larger than usual. I add 50 on the diagonal term. Okay, so diagonal term is big. What happened to the condition number? Condition number decreased from 40 to 11. Okay? So if the diagonal term is big, it's good. Okay? Large diagonal term make it easier to get the answer and get better accuracy in general. Okay, what is this? What's this about? You see, C-num test. C-num test is this matrix, right? That's C-num test. And F is Frobenius norm, which is square everything, add together, and then take the square root. That is FRO over here. So basically, I use the automatic function to calculate it. Another way, I can get norm of A inverse multiplied by norm of A, multiplied to each other, and then it should get the same thing, which is the same. How do I get A inverse? I do scipy.linalg that give me the inverse. You should know this too. Okay, just use a function. So what is Frobenius norm? Everything square, add together, and take the square root. That's for vector. For matrix, every member Aij take the absolute value square, add all of them together, then take the square root. Okay. For complex number, you may have to do like conjugate or something, but we don't worry about that too much. All right. So instead of using this, calculate norm by use the given function, you can calculate it manually. Can you? You can always do that, right? Calculate it manually. Maybe this way is better. So I use sum equal to 0 and do for I in that range, and then cnum test dot cnum test transpose dot t is transpose, right? And ij. So I try to check. Hey, norm, is that equal to square root of trace a dagger a or not? Trace is the summation of the diagonal term. So if I have two matrices, do the dagger or conjugate transpose. Take the complex conjugate, take transpose, multiply to each other, and then do the summation of the diagonal term. I get norm 2. Let's check. (183), same. So method 1, I have two nested for loop, okay, and I have sum equal to sum plus I square, and after finish everything, have sum square root, sum to the power 0.5. That's method 1. Method 2, just do the summation of the diagonal term. The diagonal term comes from dot dot, okay. Die r equal to c num test dot dot something ij. 119 is not good, especially on the row that die r or diagonal term equal to c num test dot dot. Lin, Lin, why is that? Why is not good?
Well, because just make it too much.
Diagonal term equal to cnum test dot dot cnum test transpose ii. Why that is not good? Programming wise, it gives you the correct answer, yes, but you should not put it over there, or I should not put it over there. Why? I mean, why it should not be over there?
I'm trying to figure out the code first.
The code is
Because you have to sum
I from 0 to n, kind of. I from 0 to n, get the diagonal term, then add them together. That's the code. But I'm telling you, that r equal to something something like that is not good. You should not do it. I did it, but you should not do it. Why is that? Okay, it is not the right place to put it, because it makes this thing slower than it should be. This thing is already complicated. We don't want to make it to be more complicated. Can we put it outside the for loop? None. Can we calculate A dot A transpose outside the for loop? Yes or no?
maybe if we have a predefined libraries for that
Maybe.
to calculate the
Just
transpose.
maybe. So think about this. You see dot dot, right? Period dot. And inside it has to do transpose. So you do transpose first, and then you do multiplication. How many times that it did that kind of calculation? N time, right? Do we need to do it n time? No. We can do it just once. We can do it outside. If we do like, okay, ATA equal to right hand side of that equation, that r equal to something, something, something. And then we say that r equal to ATN I comma I. So we can finish the calculation first. and then get access to the diagonal term later. That will be sensible, right? You see my point? Both will work, but this way of doing it make the program calculate transpose n time, calculate the modification n times, which is slow. Another way of doing it is just take it outside and take the modification answer inside and access just the diagonal term. That way you do the modification one time, transposes one time, and you access the result that is already done n times. You see my point?
Can you explain a bit how you got the diagonal term again?
This, with this line, right?
Yeah.
You remember the formula?
Oh.
Square root of trace A multiply A transpose multiplied by A. Dagger is conjugate transpose, but we don't have complex numbers, so it's the same as transpose. So you have A transpose multiplied by A, then you take the summation of the diagonal term, then take the square root of trace, then you get norm.
Okay.
So you can finish the A transpose A first, okay, and then you do the summation later. You can just do the A transpose just once, dot product just once, not n times. See my point?
Right.
Okay, condition number before and after partial pivoting is the same. That's what I got. Okay, let's take a look. That is just partial pivoting. Okay, it's just swap. Okay. I have this one before swapping, this one after swapping. Condition number, they're just the same. Okay, it doesn't distinguish between with and without pivoting. In the both case, the condition number does not change after row switching. Can condition number change after row switching? No, I get that answer from math stack exchange. Okay, scaling or adding with other row can change the condition number. Okay, but not just like do rows pivoting. Okay, let's take a look at P. What is P? Diagonal term, kind of 0, and the rest. So P is a permutation matrix. Okay, P is permutation matrix. It's used to switch row and column. Condition number of matrix P is 1. Same thing as a what? Identity matrix, right? Partial pivoting, if I do partial pivoting, I get diagonal term to be 1. Okay, condition number is the same. If you do modification, I have 5 over there, so condition number can change. Okay? Alright, done with condition number. Condition number is the number to tell how difficult it is to solve. Is it high? This means the answer tend to have high
It's more difficult.
numerical error. Okay. Let's do LU decomposition. I already talked about LU decomposition basic, right? The theory. Josh, you remember that? Who's a volunteer? Oh, you want to volunteer? Ami, can you explain me about LU decomposition briefly?
So we basically break the matrix A into the lower triangular matrix and upper triangular matrix first, and then basically substitute the LU with Y, or the UX with Y, and we get we know the right side and the left hand side of the matrix with the Y as the unknown. We divide the B matrix by the Y, by the L, the lower triangular matrix, and we get the y. And we back substitute it to the x value, the x matrix, to give us
So between forward substitution and backward substitution, if we use LU decomposition, what do we do first? Forward or backward?
sorry?
You have forward substitution, right?
Right.
And you also have backward substitution.
Mm-hmm.
To get the answer x, ax equal to b,
Yeah,
you said we split a into L and U,
yeah,
and then do something. This requires backward and forward
yeah.
substitution. Which one comes first?
Forward one first.
Okay, correct answer. Let me pause it a little bit.